Welcome to our exploration of feature selection methods in machine learning. Feature selection is the process of identifying and selecting the most relevant features from your dataset to build better machine learning models. In real-world machine learning problems, datasets often contain many features, but not all of them are equally important. Feature selection helps identify which features are most relevant, eliminating noise and redundancy from your model. Feature selection provides three major benefits. It reduces overfitting by eliminating noise, speeds up model training, and improves model interpretability. In this course, we'll explore different feature selection methods, categorized into filter, wrapper, embedded, and hybrid approaches. These methods differ in how they select features, their computational complexity, and their effectiveness for different types of problems. One simple approach to feature selection is analyzing correlations between features. A correlation matrix like this one from the iris dataset can reveal which features are strongly related to the target variable and which features might be redundant. In the following sections, we'll explore each type of feature selection method in detail, starting with filter methods, then wrapper methods, embedded methods, and finally hybrid and stability approaches. By understanding these different approaches, you'll be equipped to choose the right feature selection method for your specific machine learning problem. Filter methods evaluate features independently of any machine learning model. They act like a funnel, screening features based on their individual properties before modeling. These methods are fast, computationally efficient, and excellent for initial feature screening in high-dimensional datasets. One powerful filter method is C-statistic, also known as area under the curve, or AUC ranking. AUC measures a feature's ability to discriminate between classes. It ranges from 0.5 for random guessing to 1 for perfect discrimination. The AUC is calculated from the receiver operating characteristic curve, which plots the true positive rate against the false positive rate. Features with higher AUC values have better discriminatory power and are ranked higher in importance. AUC ranking is one of several univariate feature selection methods that can be applied based on the data types of your variables. The AUC ranking process involves several steps. AUC ranking offers several advantages, but also has limitations. In summary, AUC ranking provides a fast, efficient way to screen features based on their individual predictive power before building more complex models. Wrapper methods evaluate different feature subsets using a machine learning model. Unlike filter methods that assess features independently, wrapper methods use the model's performance to guide selection. Recursive Feature Elimination, or RFE, is a popular wrapper method that recursively removes the weakest features from a model. The RFE process starts by training a model on all available features. It then ranks these features by their importance. Next, it removes the least important feature or features and retrains the model with the remaining subset. This process repeats iteratively until an optimal number of features remains, typically determined by monitoring model performance. This diagram illustrates the recursive feature elimination process. We start with all features, then iteratively remove the least important ones, and retrain our model. Let's visualize how RFE works iteratively. We start with all features, and our model achieves 85% accuracy. After identifying feature E as the weakest with an importance of 0.3, we remove it and retrain our model. The accuracy improves to 87%. In the next iteration, we remove feature C, which now has the lowest importance. Our model accuracy increases to 89%. When we remove feature B, we notice that the performance slightly decreases to 88%. This indicates we may have reached our optimal feature subset. Since performance decreased, we would stop here and conclude that our optimal feature subset contains features A, D, and F. Let's review the advantages and limitations of recursive feature elimination. RFE provides better predictive accuracy than filter methods because it considers feature interactions and optimizes for your specific model. However, RFE is computationally expensive, especially with large feature sets. It also carries a risk of overfitting and produces model-dependent results. RFE works well with many model types, including random forests, SVMs, gradient boosting, and linear models. any algorithm that can provide feature importance scores. The Boruta algorithm is an all-relevant feature selection method based on random forests. It identifies truly important features by comparing them with randomized shadow copies of the original features. Let's examine how the Boruta algorithm works. First, the algorithm creates shadow features by shuffling the values of the original features. Next, it trains a random forest model using both the original features and these shadow features. Then, it compares the importance of each real feature against the importance of its shadow counterpart. Finally, it keeps only those features that consistently outperform their shadows over multiple iterations. This illustration shows how Boruta creates and uses shadow features to determine feature importance. Original features are combined with shadow features, which are shuffled copies of the real data. The random forest model calculates importance scores for all features and then compares real features against their shadows. Boruta relies on random forests, which are collections of decision trees that vote on predictions. Random forests provide feature importance scores by measuring how each feature improves prediction accuracy across multiple decision trees. In Boruta, we compare the importance scores of real features against their shadow counterparts. Real features typically have higher importance scores when they contain meaningful information. Shadow features, being randomly shuffled, should have lower importance values. Features that consistently outperform their shadows are confirmed as important. If a feature's importance is significantly higher than its shadow over multiple iterations, it's confirmed. Features with importance scores close to their shadows remain tentative and require more iterations. After multiple iterations, Boruta produces a final selection of important features. In this example, from a Titanic survival dataset, Boruta identified several key features including sex, peace-lass, and fair as most important. Boruta classifies features into 3 categories through an iterative process. Initially, all features start in a tentative state. After comparing with shadow features over multiple iterations, some features are confirmed as important. Features that don't perform better than their shadows are rejected. Features with inconsistent performance remain tentative and may require more iterations or manual decision. The Boruta algorithm offers several key benefits for feature selection. It finds all relevant features, not just the minimal optimal subset. It naturally handles feature interactions through the underlying random forest model. It provides statistical significance through the shadow feature comparison mechanism. And it reduces manual tuning with an automated feature selection process. Embedded methods perform feature selection as part of the model training process. LASSO, which stands for Least Absolute Shrinkage and Selection Operator, is one of the most common embedded methods for feature selection. LASSO adds a penalty term to the loss function, which is based on the absolute value of the feature coefficients. This L1 penalty term, shown in yellow, is what makes LASSO special. It's proportional to the sum of the absolute values of the coefficients. As the penalty parameter lambda increases, LASSO shrinks less important feature coefficients to exactly 0. Meanwhile, important features retain non-zero coefficients, though they may be smaller than in an unregularized model. This naturally leads to automatic feature selection, as coefficients that reach 0 effectively remove those features from the model. Let's visualize how feature coefficients change as we increase the regularization strength. This is known as the coefficient path. This graph shows the coefficient values for different features as lambda increases from left to right. As we increase lambda, coefficients shrink at different rates. Some features quickly drop to 0, while others maintain their importance longer. Let's move our lambda slider to see how features are progressively eliminated as regularization increases. Now, let's look at a different visualization showing how feature coefficients shrink as lambda increases. Each bar represents a feature coefficient. Initially, all features have non-zero values. As we increase lambda, watch how the coefficients shrink at different rates, with some eventually becoming exactly 0. Let's now compare LASSO's L1 penalty with other regularization approaches, like ridge regression's L2 penalty and elastic net. This visualization shows how different penalties affect model coefficients. Notice how L1 penalty from LASSO produces sparse solutions with coefficients exactly at zero, while L2 penalty only shrinks coefficients toward zero without eliminating features completely. To summarize, LASSO performs feature selection during model training by eliminating less important features through coefficient shrinkage to zero. The regularization strength lambda controls the trade-off between model fit and feature sparsity. Permutation importance is a powerful embedded method for feature selection that works with any machine learning model. With permutation importance, we start with a trained model that makes predictions with a certain baseline accuracy. The key idea of permutation importance is to randomly shuffle the values of one feature at a time and measure how much this shuffling reduces the model's performance. Let's shuffle feature 2. This breaks any relationship between this feature and the target output. When we use this shuffled feature with our model, the accuracy drops from 90% to 75%. That's a 15% drop, indicating this is an important feature. We repeat this process for each feature, shuffling one at a time to measure the impact on model performance. Features that cause a larger drop in accuracy when shuffled are considered more important. Here we can see feature 3 causes an 18% drop in accuracy, making it the most important feature. Permutation importance offers several key advantages. It's model agnostic, working with any machine learning algorithm. The method is intuitive, directly measuring a feature's impact on performance. It also considers feature interactions already captured by the model and can be used with any performance metric. For moderate feature sets, this method is computationally efficient. Stability selection combines subsampling with embedded methods like LASSO to provide more robust feature selection. The stability selection process starts with the original dataset and involves repeatedly generating random subsamples. For each subsample, we apply an embedded method like LASSO to select features. We then count how frequently each feature is selected across all subsamples and apply a threshold to determine our final feature set. Let's see how stability selection works in practice. We start with our original dataset containing several features. We create multiple random subsamples from our dataset, typically containing about half of the original observations. For each subsample, we apply LASSO regularization to select features. The diagram shows how this process works. We create B random subsamples, apply LASSO to each one, and then count how often each feature is selected. Next, we count how often each feature was selected across all subsamples. This gives us a stability score or selection frequency for each feature. We then set a threshold, typically around 60%, and only keep features that were selected in at least that percentage of subsamples. In this example, features F1, F3, and F5 exceed our threshold and would be selected for our final model. Stability selection offers several advantages. It's more robust than single-pass methods, reduces false positive selections, controls for randomness in the selection process, and works particularly well with high-dimensional data. Hybrid approaches in feature selection combine the strengths of multiple methods to achieve better results than using any single method alone. Filter methods use statistical tests to quickly rank features, while wrapper methods use actual model performance to select the best features. By combining these approaches, we can create a hybrid method that leverages the speed of filters and the accuracy of wrappers. A typical hybrid approach first uses a filter method to quickly reduce the feature space, then applies a more computationally intensive wrapper method on the reduced set. Hybrid approaches offer several benefits: improved accuracy, better computational efficiency, reduced risk of overfitting, and more stable feature subsets. One example of a hybrid approach is ant colony optimization, which is inspired by how ants find the shortest path to food. This method works by initially exploring features randomly. Successful feature combinations are marked with virtual pheromones. Stronger pheromone trails attract more exploration, And eventually, the best feature subsets emerge through this collective intelligence process. In practice, a hybrid approach might first apply a filter method like information gain to rank features, select the top features, then use a wrapper method like recursive feature elimination on this reduced set, finally evaluating and selecting the optimal subset. Stability in feature selection refers to the robustness of algorithms against variations in the training data, parameter settings, or initialization. When selecting features, we want methods that maintain consistency, like a well-balanced scale that identifies the same important features even when the data slightly changes. Stability in feature selection is crucial for several reasons. It ensures that our selected features are meaningful and not just artifacts of a particular dataset. It improves model interpretability by providing consistent explanations, and it helps identify feature subsets that will generalize well to new data. Let's compare unstable and stable feature selection methods. Unstable methods select different features when the data changes slightly, while stable methods consistently identify the same important features. When we introduce small changes to our dataset, unstable methods yield significantly different feature sets, while stable methods maintain consistent selections. Several approaches can improve stability in feature selection. These include ensemble methods that combine multiple selection runs, stability selection techniques that combine subsampling with regularization, consensus approaches that aggregate across different algorithms, and methods that explicitly penalize unstable feature subsets. To ensure stability in your feature selection process, measure stability using indices like Jacquard or Kuncheva's index, run feature selection multiple times with different data subsets, and select features that appear consistently. Always balance stability with the model's predictive performance. In summary, feature selection is essential for building accurate, efficient, and interpretable machine learning models. We've explored several feature selection approaches. Filter methods are great for fast screening, wrapper methods for highest accuracy, embedded methods for regularized modeling, and stability methods for robust selection. Choosing the right method depends on your specific needs. Filter methods are ideal for quick screening with high-dimensional data. Wrapper methods excel when maximum predictive performance is needed. Embedded methods, like regularization techniques, incorporate feature selection during model training. And stability methods ensure consistent selection across data variations. The right feature selection approach provides multiple benefits. You'll achieve more accurate predictions through focused learning on relevant features. Training and inference become faster with reduced dimensionality. Your models will be more interpretable as they rely on fewer, more meaningful features, and you'll need less storage and memory for your datasets. In conclusion, selecting the right feature selection strategy is a crucial step that unlocks more accurate, efficient, and interpretable machine learning models.